For centuries, Mars has been a beacon of mystery and possibility in the night sky. The red planet, shimmering faintly against the vast darkness, has inspired humanity's imagination, dreams, and scientific curiosity like no other celestial body except Earth itself. What secrets lie beneath its dusty, rust-colored surface? Could it have once been a world teeming with life, or does it remain a silent, barren relic of the solar system's distant past? These questions have driven decades of exploration, from telescopic observations to robotic missions. Now, the latest chapter in this ongoing saga unfolds with NASA's Perseverance rover, which has made a discovery that could reshape everything we thought we knew about Mars. The possibility of life beyond Earth is perhaps one of the most profound and compelling questions humanity has ever asked. Among all the planets in our solar system, Mars stands out as the most promising candidate to have harbored life. Its surface bears scars of ancient rivers, valleys, and lakes. Signs of past water flow are etched into the rocks, hinting at a time when the planet's climate might have been much warmer and wetter. NASA's Perseverance rover, launched in 2020 and landing successfully on Mars in early 2021, was designed with this quest in mind: to seek signs of ancient microbial life and gather samples that might one day be returned to Earth for deeper analysis. Recently, during its exploration of a deep Martian canyon, Perseverance stumbled upon something completely unexpected. Hidden beneath layers of sediment and dust, the rover's instruments detected a strange geological formation unlike anything previously seen on Mars. This anomaly is not just an odd rock formation. It challenges long-held assumptions about the planet's geology and environmental history. It is a formation that appears both baffling and tantalizing, pointing to processes far more complex than the simple accumulation of sand and dust. At first glance, the structure looks like a mosaic of crystalline layers, each one distinct in composition and texture. Scientists analyzing the high-resolution images and mineral data collected by the rover's sophisticated instruments noticed patterns suggesting the presence of unusual compounds, minerals that rarely form on Mars's surface as we understand it. These layers are interwoven with crystalline structures that resemble those formed under extreme chemical and thermal conditions on Earth, such as those found near hydrothermal vents or volcanic hot springs. This discovery forces a reconsideration of Mars not as a static, desolate wasteland, but as a planet that may have once hosted dynamic geological and possibly chemical activity. The implications are vast. If such formations can form only under specific environmental conditions, perhaps involving liquid water, volcanic activity, and chemical reactions, it suggests that Mars's ancient past was far richer and more varied than previously thought. This, in turn, raises the thrilling possibility that such environments might have been suitable habitats for primitive life forms. The rover's detailed analysis of the formation indicates that it is unlikely to be the product of ordinary sedimentary processes. Instead, researchers speculate that it may be the residue of high-energy events, such as impacts from meteorites or intense solar radiation, combined with chemical transformations in the planet's crust. This hypothesis aligns with the idea that Mars was once subjected to dramatic shifts in temperature, pressure, and chemical composition, creating niches. One exciting aspect of this finding is the potential link between these mineral formations and past hydrothermal activity. On Earth, hydrothermal systems are known to support rich ecosystems, fueled by chemical energy from volcanic vents rather than sunlight. If Mars once had similar hydrothermal conditions, even briefly, it could mean the planet was home to microbe-friendly environments that might have persisted for thousands or even millions of years. The discovery has sent ripples through the scientific community. Planetary geologists, chemists, astrobiologists, and astronomers are all eager to study the data further and develop new models to explain how such formations could have formed. This interdisciplinary approach highlights how modern planetary science transcends traditional boundaries, combining multiple fields to unravel the complexities of other worlds. Moreover, this finding adds a cosmic dimension to our understanding of mineral formation. If the processes detected on Mars occur elsewhere, on moons, asteroids, or even exoplanets, it could suggest universal mechanisms at work, shaping planetary surfaces throughout the galaxy. The tantalizing possibility that these mineral structures could be markers of past life or habitable conditions raises the stakes for future exploration missions. To fully understand the significance of the discovery, it helps to dive deeper into the nature of the formation itself. The rover's instruments revealed layers composed of silicates interspersed with sulfates and carbonates, minerals often associated with aqueous environments on Earth. The crystalline structures exhibit unusual geometries and compositions, hinting at chemical reactions that may have occurred under unique circumstances, perhaps triggered by the interaction of volcanic materials with subsurface brines or by sudden temperature fluctuations caused by meteorite impacts. Such processes are rare and complex, making this formation a geological anomaly worthy of intense study. It serves as a geological archive, preserving evidence of a chapter in Mars's history that has remained hidden until now. Understanding this formation could unlock insights into the planet's transition from a warmer, wetter world to the cold desert it is today. In addition to reshaping geological paradigms, this discovery also offers profound astrobiological implications. The presence of water-related minerals suggests that Mars had the ingredients necessary for life, at least at some point in its history. Although the current Martian environment is hostile, with its thin atmosphere, intense radiation, and freezing temperatures, the ancient conditions implied by this formation might have been quite different. If microbial life ever arose on Mars, it would have had to survive in environments capable of protecting it from harsh surface conditions, perhaps underground or near geothermal sources. The discovery of such mineralogical evidence lends credence to the idea that the building blocks of life could have been assembled and preserved on Mars in these protected niches. Furthermore, this finding encourages scientists to rethink the criteria used to identify habitable environments beyond Earth. Instead of focusing solely on planets that resemble Earth today, researchers are broadening their horizons to include worlds that may have undergone dramatic transformation